I'll spend a few minutes and talk about a structure where supply and demand operate through price, and it creates a structure that is essentially an indecision systems archetype. If we begin to look at the structure, it's actually two balancing loops. The first one being a balancing loop where the goal is whatever is defined as the demand, and it is this balancing loop that attempts to to bring the supply into alignment with whatever the demand is, so that there is no more price change influencing this structure to try and produce a balance. The second loop uses supply as the goal and tries to bring demand into line with whatever the supply supports in terms of price. So that from these two loops interacting together simultaneously, depending upon the delays that are in the structure, this tends to oscillate back and forth. That can be readily seen if we look at the stock and flow simulation version of this model, where we have supply as a stock, and this is the first balancing loop. Demand is part of the second balancing loop. We've also added a factor, which is just a variable between 0 and 1 that allows us to control the rate that the change interacts in the model, and the price, which is a unit price plus or minus the change that's happening. And if you look at a number of the systems archetype models that I build, I tend to build them all around a values between 0 and 1, so that I can focus on the implications of the interactions as opposed to thinking about what the actual values are. So this starts out with supply as 1 and demand as 1, and I get this set wrong, and the price being a unit of 1 and the factor being 1, and there being no delays in the system, just to give me some place to start with. So when I run this, it's about as exciting as watching paint dry, because the price is unity. There is, in fact, no change, and supply and demand are both at 100%. Whatever the real values tend to be is irrelevant at this point. But what I want to do is to say, well, suppose that the demand drops to 75% of whatever it was. If I then go ahead and run this simulation, what it shows me is that as soon as, because there's a difference between supply and demand, the price begins to drop because demand is down. But as the price is dropping, the supply is also dropping, trying to come into balance, and at the same time, the demand is increasing. So you can see that the change started out at some value but quickly restabilized, so that there is no difference between supply and demand. They've restabilized at a new value. And as we continue to look at the effects, now suppose that I introduce a delay into this model and say that this the time that it takes for the change in supply to be recognized in this equation is delayed by 50%, and I go ahead and run this again. You notice that there's some wiggles that show up in the model, and that's because of the period of time it takes for the change to actually be realized. And as delays in the system increase, let me add a delay over here in this part and run it again. You notice that the price is oscillating. It's the wrong diagram. Where's that? Oh, I think I just got rid of that diagram. Hold on. The price is. What am I doing? Oh, this turns them off. I forgot about that. The price is oscillating back and forth, but it is in fact beginning to smooth out as the change is beginning to smooth out. It's a dampened oscillations, but if the time delays tend to get large enough, what you find out is that the system actually gets out of control, so that that based upon the system reacting to what it thinks the changes are and not being aware of the real changes until some time later, the system ends up overreacting, trying to compensate for what it did previously that it shouldn't have done. And the way out of this in a structure with delays in it is to in fact realize that overreacting is not a good thing. So that if you change the value of this factor right here, which controls the rate at which this change interacts or causes it to change the values of supply and demand, where this is the situation, if we change that factor to 90% and run this again, you'll notice that the model is beginning to be less out of control. If we change this to 75% and run it again, you notice that the model is now sort of oscillating back and forth at the same degree on an ongoing basis so that it's relatively stable, and continuing to increase this, you find out that at 50%, so that because we understand that there are delays in the system, the approach to dealing with the problem is either stop overreacting to the changes because we know that there are delays in the system and we don't know the extent of the changes, so we have to stop overreacting, or figure out how to take the delays out of the system so that we in fact have better information to deal with. Actually, the structure boils down to patience is a good thing, so as to not overreact with the changes that you sense because you know that they're not the actual values. So this model is available on the focus page so that you can play with it and interact with the model and see get a better sense of how changing these values in fact alters the way that the system operates on an ongoing basis. So hope you found this of interest. Bye.